Okay, so let's find the K value for some springs. I'm going to start off by grabbing my ruler and lining it up with the bottom part of the spring. So that's going to be at my 0 position. I'm going to grab a 250 gram mass, attach it to the spring. Now when you let it go, it actually starts to oscillate up and down, which is not what we want, so I'm just going to hit the stop sign. So what this does is allow the mass to go down to its new equilibrium position. This is where it would go if you very gently were to lower it until it stopped going down. So we need to take a look at the bottom part of the spring, and that is at the 4 centimeter mark, which means our delta X is 4 centimeters, and we have a 250 gram mass, so we will use that to determine our K. Okay, so now to do our calculation for the spring constant, I've made a bit of a free body diagram. We had our 250 gram mass, which is equivalent to 0.250 kilograms. We have gravity pulling down and the spring pulling back. So as we know, gravity is m times g, which in this case is equivalent to the mass, 0.250 kilogram, times g, which is 9.8 newtons per kilogram. And when we calculate that, we get 2.45 newtons. So that is the gravitational pull down on the mass. Now the spring pulling back up, we're going to look at it in terms of the absolute values of the forces. So if we have a total downward force of 2.45 newtons and the spring is in equilibrium, that means that the spring is pulling upwards with a force of 2.45 newtons. Fx represents the force of the spring. And the equation for force on a spring, I'm going to be using Fx equals Kx. I'm not putting in the negative. Again, I'm just looking at the absolute value of the numbers. So we actually have an Fx. So we know that the force on the spring is 2.45 newtons. I'm trying to solve for the K value, and the displacement of the spring was 4 centimeters. So now I'm just going to divide both sides by 4 centimeters on the right-hand side. That cancels out, and then we're going to be left with K is equal to 2.45 divided by 4 centimeters. That gives us 0.6125 newtons per centimeter. Normally the K value is in units of newtons per meter, so we'll just convert that, which would be 61.25 newtons per meter. And if we go to our 2 sig digs, it would be 61 newtons per meter. Okay, we're also able to calculate a spring constant. Instead of stretching the spring, we can do it by compression. So here's our situation. We have a spring in a vertical position with a pan on top, and here is a 500 gram mass. 500 gram mass is going to be placed on the spring, which will cause it to compress. Okay, so we're going to use the ruler to measure from the pan to the top of this black box, and we can see that it is 4.5 centimeters. I'm now going to place the mass on top of the spring, and it will compress down, and then we'll take our new measurement. Okay, so now that the mass has been placed on top, it's compressed the spring down, and our new displacement is 2.1 centimeters. We started at 4.5 centimeters, and now we're at 2.1. Okay, so just like with our last free body diagram, we've got our mass, we've got, in this case, gravity is pulling down, but the spring will be pushing back up. So we need to calculate force of gravity, mg, 0.5 kilograms times 9.8 newtons per kilogram, which gives us 4.90 newtons. So if gravity is pulling down with 4.90 newtons, so the spring has to be pushing back with 4.90 newtons. Now let's calculate our K value. So Fx equals Kx. Our gravitational pull downwards, or the spring force pushing back up, is 4.90 newtons. K value times the initial length was 4.5 centimeters. The compressed length was 2.1. Subtract the two numbers to get 2.4 centimeters. Then, just like we did before, divide both sides by this number. So 4.9 divided by 2.4 is going to give us 0.4897 newtons per centimeter. Let's put it into newtons per meter, so that'd be 48.97 newtons per meter. And only going to 2 sig digs would give us 49 newtons per meter. So you are able to calculate the K value of a spring, either being stretched or compressed.